problem of clean energy is only half a problem. The other half is we got to move the energy from where it's created to where it's needed. Given how hard it is to build new transmission in the U.S., there's no way that we're going to double the capacity of conventional AC high-voltage grid in the next few decades. So here are 6 ways to do that, and I'll say a word about each of them. There's a 7th issue, of course, that's not listed on this slide, which is that we could move the demand to where the energy is being produced.
We want to be greenhouse neutral in 2045, and we want to phase out of the coal-fired power plants and the nuclear power plants. If we need renewables, then we also need the infrastructure to bring the energy to the customers. So we also need the transmission lines. This is where I often have talks for the public to really explain, yes, we need the transmission line, we cannot avoid them. So we need flexibilities and storages to balance the fluctuation. This is one big point. And the second point is that our network, it will be faster due to the missing inertia. And our research is that we do not want to stay with those point-to-point connections. We want to have a DC grid, which is also operating in parallel to the AC grid.
The focus is digitalization, decentralization, decarbonization, and there are 4 companies that have spun off from what we're doing as an example of solutions that are actually being deployed on the grid and actually making a difference, we hope. And therein lies part of the problem, right? So this is an irreversible energy transition. We're seeing very fast growth within each of the silos. There's no coordination whatsoever between them, and they all connect to the grid. So we see, a massive change that's being driven by lower costs that are really coming. What has also, made this happen are what I would call forward-leaning policies. Started to see that, fleet operators, data center operators, they're all starting to put local generation to feed their loads. So yes, there is a paradigm shift underway. Okay, we're going from grid as a resource to grid as an ecosystem. So I think there's a role that the national academies have to play out here. I think it's really important. Okay, I think we really have to help raise the level of understanding where the gaps are and what industry needs to do, and to ensure that we take a holistic view of the problems that are there.
I will also discuss the topic of power system dynamics. I will do it from a completely different approach. But with great complexity, we lose the fundamental understanding of the grid. We try to study simplified dynamic models analytically, and we try to, by that, gain a better understanding of the fundamental design principles of the grid. So here is some several open questions in this field. Of course, it's driven by practical questions. So most fundamentally, what control mechanism should be implemented in electric machines and in power electronics-based inverters? We know that power systems today are stable systems. We see it, of course, every day they operate. But we do not understand why. There is no fundamental reason, mathematically, of course. I will touch very briefly on the modeling problem. So the major question, what model is simple enough, yet it is detailed enough? So the result tells you, make the system sparse enough that this matrix H becomes positive definite. If you do that, at least based on our crude modeling, then this operating point will be stable.
Electric power grids derive their stability and reliability through their sheer immense size. Fundamentally, we need good, accurate models to run the grid, because things propagate through the system faster than we can control them. And so the real focus of my presentation is going to be talking about advanced measurement systems that can be used to gather data from the grid when disturbances occur. And these wide area measurements that I'm referring to, the real enabling technology was low-cost, ubiquitous time synchronization. The significance of this is the bottom plot, the blue line. That's what the computer model predicted should have happened. If the model is that inaccurate, we can't reliably run the grid. And that is one of the contributing causes of this particular blackout. And as we migrate into more of these inverter-based resources, we need higher data higher sampling rate data to really understand that.